Ted has a BS in mechanical engineering and an MS in metallurgy. Ted retired from the Kentucky Transportation Center in March of this year, but he still assists the Kentucky Transportation Cabinet on a part-time basis. And one little tidbit about Ted that I kind of threw in there because I know Ted's history. From 1996 to 2013, he was a key leader of something called the Midwest Bridge Working Group, which was sponsored by Northwestern University, and was a collaboration on bridge and bridge preservation issues. So his group, the Midwest Bridge Working Group, was sort of a precursor to our own Midwest Bridge Preservation Partnership.
Good afternoon, everybody. Today I'm going to discuss investigations that we performed for the Kentucky Transportation Cabinet of Fractures on 3 Kentucky bridges, steel bridges, and we're going to go briefly review the work we did, our findings, and then discuss what those findings seem to indicate. The first bridge we'll cover is a interstate bridge in south central Kentucky. It was built in 1966. There's actually an identical bridge built in the other direction. It's a continuous welded steel girder structure with 4 girder lines, moderate spans, the longest one 200 feet. Just a pretty unremarkable bridge. It was made from ASTM A36 carbon structural steel. It was built in '66, so it predates the AASHTO fracture control guidelines. The recent traffic count was 18,000 vehicles, and I don't have a percentage trucks, but I know it's probably around 6 to 10%. On both bridges, there were fractures, girders in the center spans back in 2012. And then in 2014, there was a fracture in the center span of the northbound bridge. Now, this shows the cracking that occurred back in 2012. You're looking at, this is actually an interior girder from the center section looking outward. And you can see the shape of this crack is kind of unusual. It curves. And usually cracks go straight up and down. If you take a look at the northbound or the southbound bridge, you can see the reason for the curvature. This is the crack that formed in that bridge, and the curvature is because the crack goes through this narrow gap detail here between the vertical and the horizontal stiffeners. If you look, the fillet welds that attach the vertical stiffener and the horizontal stiffener to the web are in close proximity to each other, and they probably touch. We actually didn't work on this particular fracture case. The cabinet was anxious to get it repaired, so they fixed it, and then they told us about it later. They came in a year later and asked us, well, what's your opinion of this thing? Why did it crack? Immediately we jumped on this detail in this area. A horizontal stiffener, category E fatigue detail, a lot of traffic over the bridge, fairly old bridge. So we thought, fatigue could be an issue. Then we considered the fact that the welds were in close proximity to each other, those vertical and horizontal fillet welds. We thought, well, potentially we could have constraint-induced fracture. After this, we did some reviews, and we ran across this. This document was from the Illinois DOT back in 2010, and they came up with some nice pictures of some weld details that could be involved in constraint-induced fractures. The one on the left there is the infamous hone detail, and the one on the far right there is basically pretty similar to what we had in the field. You can see this this stiffener's clipped there, but I think that was done for photographic purposes. These things usually are squared off on their ends. The one thing that I wanted to point out here, the key issue is this quarter-inch distance between the vertical and horizontal fillet welds. The guidance indicates that if that distance is less than a quarter inch, or if the fillet welds are touching, then you could possibly get constraint-induced fracture. That's a result of the fact you have triaxial stress, tensile stresses, and they inhibit plastic redistribution of stresses in that gap area there, and you can have what's called a pop-in fracture, releases a lot of strain energy, and if the circumstance is right, it can fracture a whole girder, or if there's not enough energy available, it can run for a bit and then arrest. Well, here we are in 2014. This is a northbound bridge. Same girder that the fracture occurred in 2012. It's one panel point over, about 25 feet away. And we can see that another similar fracture has started. And you can see on the upper portion there, the crack is arrested in the web. And on the bottom portion, it's jumped parted the web completely and jumped into the lower flange. There you can see that a pretty large crack in the lower flange, which is an area of concern. So we talked to the cabinet, and they wanted us to look at this thing. So anyway, the cabinet talked to us about being involved to analyze the failure. I got it, this should back up. So we said, well, could you please cut out this area and give us the end of the horizontal stiffener and the crack surfaces there, and on one side also give us this transverse stiffener. And so as part of the retrofit, they cut those pieces out and gave it to us for failure analysis. And I want to say I work with a really good failure analysis person. I get my finger into it, but he's really expert. So any of this that's done good, it's his credit, not mine. And moving forward, what you have here is the portion of the fracture surface. This is the web, and this is that horizontal stiffener. And you can see this gloppy fillet weld that attaches the horizontal stiffener to the web. And if you look at this fracture surface, it's pretty grainy, typical of a brittle fracture in steel. And a lot of times when you have these brittle fractures, you generate this chevron pattern, okay? And the chevron, there'll be concentric chevrons, and they'll point back to the source of the failure. And in this case, he put some yellow showing the direction of crack propagation, but the chevrons were pointing in the opposite direction. So what we can see here is basically the crack started at this point where this red arrow is and ran up, and it ran down concurrently. Optical view of this detail, a little greater magnification. I think you can see these chevrons here a little bit clearer, but the point of interest is this little thumbnail detail, and that seems to be the point where the fracture has originated. So anyway, what we did as part of our failure analysis is we cut that area out, and then we put it into a scanning electron microscope. And this is what you see at about 35 magnification, power magnification. In this area here in the picture, you see this grainy area that's got what he calls brittle cleavage cracking, which meant that the crack was running in that area. In this little thumbnail, he says, is a fatigue failure. And he says also you have these little marks along here. He calls those ratchet marks for major stops and starts in the crack as it moves. That's interesting enough, but the other thing of interest is this. This is the scale that sizes our details that we're looking at. That's 1 millimeter. So what we're seeing here is a thumbnail, which is a fatigue crack, that is 1 millimeter deep and 5 millimeters long, and that's the critical crack size to instigate unstable brittle fracture. Because when that happens, boom, that big crack appears really quick. That small fatigue crack may take a long time, like 60 years, to get to that point. And just as a little note here, I wanted to show you this. If you ever went to materials class that talked about steel and fatigue, they always mentioned the thing about fatigue striations, okay? To see those, you really have to kick the magnification up at least 2,000 times. And this picture here is at 5,000 magnification of that thumbnail area. Just to verify that's a fatigue crack, you can see these little steps here, 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 here. Those are fatigue crack striations. That's where a crack stops and grows in one load cycle. And for steel, structural steels, they're not very well defined like some other metals. And you have to sometimes search for fatigue crack striations if you're trying to determine if that's the cause. And this next picture is at about 1,000 magnification, and this is the portion of the fracture surface where we had brittle fracture. This is what you see here is called cleavage cracks. It's where cracks ran across grains. You can see maybe the outline of the grains here. They didn't deform, they just sheared. They broke, they pulled apart. They didn't shear, they just separated. These are low energy fractures, and that's why you get so much crack propagation with unstable brittle fractures. So what were our investigation findings? Well, we know that unstable brittle fracture started and it ran from a little fatigue crack 1 millimeter deep by 5 millimeters wide. Performed tests on the A36 material. We looked at the physical and mechanical properties, did some tensile tests, did what they call EDS, which is a spectrographic method to check the elemental content of the steel. And we found that it conformed to A36 structural steel. We didn't have quite enough material. The plate was only 3/8 of an inch thick, so we couldn't do a full thickness Charpy. We did a subsized, we had enough material for one subsized Charpy, and we ran it at the zone 2 temperature requirement, which covers that bridge. It's non-fracture critical, and we got a very low value, about 6 or 8 foot-pounds. And we were kind of alarmed at that. And then somebody says, well, you've got to resolve that to what you get in a full-size specimen. And there's equations for that. And so once we took that value and ran it through the equation that accounted for the reduction in cross-sectional area of the specimen, we found out that the steel was plenty tough. So even though it wasn't built, it wasn't obtained to a fracture toughness guideline, it met the one that applied for that particular application. Then we were somewhat in a quandary here. We're looking at this crack that's very small, and we really kind of don't believe that on its own it started such a big brittle fracture. It had to have some help. So maybe the constraint-induced fatigue was we had constraint in that area, and maybe that helped promote the brittle behavior of the steel and gave us what we got. we're not sure. But anyway, we got this category E detail that says fatigue, and we got the type of detail and the fact that the fillet welds touch each other. So it could be CIF as well, or it could be an interplay of those two. We couldn't really tell. And then the last thing is, as we were investigating this out in the field, we were monitoring the growth of that crack in that flange, and it had grown like maybe 3/4 or 3/8 of an inch in about a month. So basically fatigue was chewing through it, and they had to promptly repair the girder before that lower flange parted. Our next bridge is an overpass structure in southern Kentucky. It was built in 1978. If the other one was unremarkable, this is more unremarkable bridge. It's shorter span, only 120-foot main span there, continuous steel girder structure, 4 girder lines, also A36. Now, when this was built, there was the AASHTO fracture control plan in place, so it had to meet Charpy impact test values, the steel did. Issue of traffic. We were over on this bridge for the better part of a day. There was literally no traffic on that bridge. I think it would be exaggeration to say 10 vehicles crossed it while we were there. And they were all like pickups or cars. So I don't think the traffic count on this bridge is normally more than a few hundred vehicles per day. Twin cracks were detected in the fascia girder of the bridge in 2016. And these occurred in the negative moment area over a pier. And here is our overpass bridge. You can see it's got 2 piers in the median area there. Just a pretty commonplace run-of-the-mill structure. This is a Google Earth picture. And what's interesting is that it was taken after the repair. And if you look hard enough, you can see where they put in the bolted splice plates over the cracked girder. We got 2 horizontal stiffeners on the fascia girders. Kentucky likes horizontal stiffeners on fascia girders for aesthetics, if nothing else. We got a crack here that didn't quite make it to the upper flange. Then we have a crack here that interplayed with the top crack, but it also ran down and it had jumped or was jumping into the lower flange at the time of the cabinet's investigation. They took that picture. So they asked us to inspect this and see what we could find. So we go in and we say, cut this out and cut this out. Category E fatigue details. Let's check it out. Here's the cross section with the fracture surfaces, actually both sides. This is the horizontal stiffener side of the web, and this is the other side for the upper stiffener, and this is for the lower stiffener. And we can see that things are pointing to the spot here where this gloppy termination of that fillet weld is on that one, and identically to near the termination of the fillet weld that attaches the horizontal stiffener to the web over here. Okay? So similar features, kind of similar to what we saw on the last bridge here. Got in and did a little scanning electron microscopy. This is only at, I think, 15 magnification. And what do we see? Well, we see something pretty much similar and somewhat similar to the last bridge in a way. We see this artifact here and this one here, and they're roughly the same size. They're not big. They're about 5 millimeters again, and maybe a millimeter deep. I don't know. We looked at these areas closely. I don't have the pictures here. They were dimpled, but we couldn't find any pronounced feature that said exactly these things are fatigue failures. And of course, you got this rough area in here and rough area in here that are brittle cleavage fractures. The question is, we're sitting there, well, it's probable fatigue, on a bridge that's got 400 or 500 ADT at most. What's going on here? Then we went back and looked at the cabinet's pictures, and we start getting a clue. The first thing is to look at this paint that popped off around this upper stiffener right there. That indicates there was fairly high strain, distortion in that area that caused that paint to come off. And we see a little bit in this area here as well. Then we look at this picture, and we've got lateral distortion in the fracture, in the web. That takes a lot of energy, a lot of stress to cause that. It probably didn't distort and fracture prior to it didn't distort like that until the fracture occurred, but there it is. So it looks like a lot of stress has been put on this bridge. But, what we saw firsthand didn't seem to support anything like that. Well, let's talk about the findings we have. The girder had unstable brittle fractures in the web, and they initiated at 2 5mm by 1mm, probably fatigue cracks, kind of deja vu from the other bridge. We did testing on the steel. We expected everything to go satisfactorily in terms of the elemental content, the tensile properties, and the choppy toughness, and it did. And our target value, of course, is at 15 foot-pounds at 40 degrees. Category E fatigue details at the stiffener termini. We got very small initial critical crack sizes. We would think that it's probably fatigue, but there's no constraint. There's no CIF featured near there, so what's going on? And so we did a little bit of investigative work and called the local county ag agent, and things suddenly became clear. You have I-24, you got grain elevator, you got 20, 30, 40,000 acres of grain field on the other side of I-24. You got one bridge, Bush Road, that connects the two. He said that agriculture is all grain. It's corn, soybeans, and sorghum, molasses, I don't know what. He said they have 2 crops a year. They load heavy semis, and I know the loads can go upwards of 140,000 pounds, whatever they can. Nobody's there to stop them. And then light goes on, and we figure out, well, that fatigue was low cycle fatigue. When you get low cycle fatigue, it looks a lot of times it just looks like tensile test. You can't see striations or beach marks or anything, and that's basically what we were seeing. We think that the fatigue was due to these periodic heavy farm to grain elevator loads, and we think because of the distortion in the web that we saw, that the girder was very heavily loaded at the time of fracture. So it may have had a truck on one side of the pier, heavy truck on the one side and a heavy truck on the other, or maybe 4 of them, It was a straw that broke the camel's back, proverbially. So now let's go look at our last case here. This is a state bridge in central Kentucky over a river built in 1960. Again, this is a relatively unremarkable bridge. In a lot of ways, it's similar to others. It's a continuous welded steel girder bridge with 3 spans with 4 girder lines. Longest span is 170 feet, intermediate from the other 2 examples. Nothing to get excited about. It was made, 1960 predates the A36 spec. This was a temporary specification that came out, A36, A373, I didn't show it, -56T, which was structural steel for welding. Obviously, there's no fracture requirements, going back that long. I will say, though, that it was welded in. There was some notes for weld inspection on this bridge. The traffic count was intermediate probably with the two bridges, 1,800 vehicles and 6.5% trucks, just what goes on a state route. There was a fracture found on the interior, one of the interior girders, and the bridge was inspected in 2017. Nothing showed up. And then a boater goes under the bridge in 2018 and looks up, and a girder's fractured. He calls it in. And this happens a lot of times. If you go back to the old famous I-79 fracture of a twin girder over at Neville Island near Pennsylvania, Pittsburgh, that was found by a tugboat captain, as I remember. Well, anyway, the cabinet sent some people out, and this is what they see. The girder had fractured 14 foot from the center line in the main span. It was located in this area. There's a thickness transition from 1 1/8 inch to 1 3/4 inch. There's a weld in there in that lower flange. And then we can see the crack ran pretty straight this time, and it hit this flanged web fillet weld up here, jumped that, and went a little ways into the upper flange, and it arrested. At this point, the cabinet said, we got to fix this thing. So we never got a chance to touch most of the fracture work. They bolted it up, but they did cut off a little piece of the upper flange, and they gave it to us and said, hey, test this for properties, it's an old steel, see what the toughness is, and the mechanical properties and stuff, and that's all you got to work with. You can't do any failure analysis because it's fixed. A little bit of frustration there on our part. And then we go back and start looking at their pictures. And then, fortunately, they took a few pictures, and we got to see a few things. And we look at this fracture surface here that's shown in this picture, which has the fortunate inclusion of a scale of a ruler, and we see something in here. And the rest of this is just a rough, grainy fracture, typical of what you think an unstable, brittle fracture looks like. But what's that in there? Magnify it, and you can see this fracture, this detail is located in the butt weld, obviously, and it's adjacent to the web to flange fillet weld. It appears to be semicircular, called half-penny crack or elliptical, we don't know, but something like that. And it's up from looking at the ruler, we estimate that it's about 3/4 of an inch wide and maybe 3/8 of an inch deep. And as we noted, the surface texture doesn't seem to match. The rest of it's irregular and grainy, and this is somewhat smooth, and we have these lines that a person could think would be beach mark. Not a lot to go on, but you run with what you got, So my failure analyst and I came to the mutual conclusion that's a defect. Well, let's look at the overall issue of any structural detail coming into play here in that area. Transition weld is category B, flange to web fillet weld, category E. The run out, the endurance limit at over 2 million cycles is 16 KIPS, KSI per cycle. Not likely to be caused by a weld detail. So we thought, well, it's a flaw. I decided, well, we know what the final size is, and based on the final size, we can calculate the weld toughness. And we sat down and we looking at the ADT, we backcast it over the life of the bridge and came up with a number of load cycles roughly based on the number of trucks that went over the bridge, about 1.5 million we figured over the life of the bridge. And we had some stress data, live stress data that we had taken on a coal haul, extended weight coal haul route, several of them, matter of fact, back in the mid-90s. And we had some equivalent stress, live stress values, and we thought, well, let's play with them. And so I got into doing something I've never done much of, which is fracture mechanics, and I had to get into calculus, and I found out I was as bad today at calculus as I was when I was going to school, but we came up with some answers. Here's the fracture mechanics equation. It relates a value called the critical stress intensity, K1 max in this case. You have stress there, you got crack depth there, there's some shape factors, I believe. And this is a crack growth equation that was derived by John Barsom and Stan Rolfe, who had basically come up with the fracture control plan criteria that AASHTO still uses today. And this particular number is relevant for the carbon steels. And you can take this K value and plug it in and do some integration and stuff, and you come up with this equation number 3, and we can plug in our live stress values, delta sigma. We can plug in then the final crack size, which we've measured, and then we can also, we know what our N is. It's this 1.5 million approximate stress cycles. We had several stress ranges we wanted to look at. The typical stress range when we did all these bridges back when in the 90s was about 3 KSI per cycle, equivalent minor stress. And if we plug that into the equation with the rest of these numbers, we figured out that the initial crack size was only about 0.35 inches. And then for the larger stress range, we find that the initial crack size should be about 1/4 of an inch. 3/8 to, I mean, 1/4 to almost the final fracture size. And those are flaw sizes that any NDT operation in a fab shop using radiography or ultrasonic testing should pretty easily detect. What are our findings? The girder, again, had unstable brittle fracture initiated from a defect in the lower flange butt weld or the flange to web fillet welds. We did mechanical testing on this. We had a lot of steel plate there. It was only the base metal to go on, of course, but we found that it met all the physical and mechanical properties met ASTM A373. We did full-size Charpy tests, quite a few of them, and we found that the steel met the Zone 2 fracture requirement for redundant bridges, again, 15 foot-pounds at 40 degrees Fahrenheit. And we found for the details that were present, basically they were just attachment welds to the major pieces. The stress ranges were too low to cause fatigue initiation due to weld details. So we're only left with the possibility that what we saw as that artifact we saw in the middle we thought was a weld defect is a weld defect. Probably came out of the fab shop. Now this was done in the 60s, and the 60s and 70s for fab shops, I've heard a number of people say it was like the Wild West. You know, things were fast and loose. And there was a lot of sloppy welding and blasé inspections, and stuff got out the door. You know, we have a number of bridge problems that have been out there for years that seem to attest pretty much to that. There was gradual We think there was gradual growth of this weld flaw by fatigue to critical size for unstable brittle fracture that ended up basically almost parting the entire girder. One other thing too, if you find a weld defect on a bridge based on this assumption that things can be missed if people aren't doing right or paying attention, if you find one defect, more than a random possibility, there may be something else lurking about in the steel there. Based on those three factors, let's just go over the differing factors. The bridges had different traffic volumes, from a few hundred vehicles to almost 20,000. Loading, you had the Kentucky route, probably pretty light loading, and for the most part, the overpass bridge was until harvest season, and then the interstate probably got pretty heavy loading, 18,000 vehicles, and I'm sure it had more than a few overloads over the top of it too. Causes of the fractures. Well, if we look at constraint-induced fracture, the only thing we can say it's a possible contributing factor on the I-75 bridge, even though that's a qualifying CIF detail. There were Category E fatigue details, ends of horizontal stiffeners that play in 2 cases. There was only 1 case of a weld defect. Now the common factors. Bridge type. They were all the same type of bridge. They were continuous girder, 3-span, 4 girder line bridges, welded construction. Service lives, they were all between 40 and 60 years old. They all used carbon structural steels, and all of those steels met current ASTM and AASHTO requirements, and should I say also did the Hone Bridge back in 2000. The other thing we see is that small crack sizes seem to be able to initiate unstable brittle fractures that can basically part or almost part these girders. The implications. It seems like if we've seen plenty of carbon steel bridges where you got, a fatigue crack you could see, you could get to it and fix it. But we got 3 cases in a row here where we have, and we've seen the circumstances may be extreme, I can't say, but we've got 3 cases in a row here where we've got cracks that are basically visually uninspectable, even at arm's length. I defy anybody to detect any of these. Unless you got a lot of rest bleed or something, by visual inspection, it ain't going to happen. You can use non-destructive evaluation, eddy current, maybe mag particle, in some cases ultrasound. If we're using inspection method, if we're relying on visual inspection, our only safeguard is going to be structural redundancy. That's it. You go out, and when we had the I-75 cracks, we told the cabinet, they said, we're going to look at it once a month. And I said, good. All you're going to do is you're going to go out and see a cracked girder. That's all you're going to be able to find. Girder fractures incur costs. You have to do reactive maintenance. Sometimes in a very short order, and things get expensive. If you close a lane on an interstate bridge to keep traffic from driving over a cracked girder, you can back up a prodigious amount of traffic. Potential risk of collapse, there's no history of that I know of in the U.S. The Hone Bridge was a 3-girder bridge. It came close. It had 2 complete girder fractures, and the 3rd girder had a crack 30 inches long in the web. Somebody saw that right when the deck started to sag, and they closed the bridge immediately because they were a state trooper. There is a case in Australia where a 4-girder bridge collapsed for 15 months after it was opened, and it had the same structural detail at the same location across the bridge, and they failed in cascading order. And but it's kind of an outlier for a number of reasons. Other actions are going to be needed to prevent further incidents that we've seen. And our concern, firstly, probably goes to bridges with fracture critical members, and secondarily, those with fatigue-prone or CLAF details. For Kentucky, we foresee some proactive steps to address the situation. First thing you got to do is look at your inventory. We have 859 steel bridges that were built between 1955 and 2000 that are of concern. And the question is, why those dates? 1955 is when Kentucky started using welding. Okay, we haven't seen this issue with riveted bridges, this welded bridges. And right at 2000, by policy, the cabinet quit using A36 steel and went over to 50 grade steel exclusively. So this is the time interval and the number of bridges that potentially qualify for bridges of concern. Currently, we are engaged in an SPR research study identifying bridges with CIF details for the cabinet. We're about pretty close to wrapping that up. In the past, we went through and identified all their quenched and tempered steels and potentially problematic high-strength, low alloy steels as well. The issue of this arm length inspection needs to be studied a little bit. You know, when can you get away with it, and when really something else need to be used. We do anticipate future work to identify fatigue and fracture prone details. Average age of our bridges is about 46 years, so it falls in that 40 to 60 category we saw for the 3 fractures we encountered. What do we do about hidden weld defects? Okay, how do we address those? That bridge that we had over that river had 64 of the same transition welds. And the cabinet looked at the scope of doing NDT on those, and they said, well, we'll just run with it. And so we've got a number of issues you can put in a bag, I guess, and look at them together, but we think that some form of prioritization is needed to focus on future work, whatever that's going to be. And with that, I'm through with my presentation. If anybody's got any questions, I guess we're done.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.